Today we're going to present about our pattern identification and exploration of Kaprekar routine. My name is Kana Samuel Jasmine.
And my name is Brian Giovanni Halem. Okay, so what is Kaprekar's routine? So basically, we pick any 4-digit number, we arrange that in descending order, and we can set that as x, and we arrange the same number in reverse order, and we subtract the numbers from each other, and we repeat this process until we reach the constant 6174, and this is true for all 4-digit numbers. However, the process can be done for other number of digits, but it might reach a loop instead of a constant.
So first of all, our goal here is to identify the patterns within the Kaprekar routine, and from that we also obtain the number theories within it. So first of all, we analyze the constant and the possible result it produces from the Kaprekar routine, and from that we graph out a result and evaluate it.
So there are two different interpretations when we analyze the Kaprekar routines. So there are 705 different combinations of 4-digit number that would produce a different set of results. And if we use those combinations in the equations, as you can see, the largest digit minus the smallest digit must be greater than or equal to the number in between, difference in between, then there are only 54 different possible combinations after the first iterations. As a result, the number, as you can see, has decreased, and it suggests a convergence might occur in the subsequent iterations, and for 4-digit it does, and it will reach 6174.
So for second interpretation, after interpreting the borrowing method there, we get that the first and last digit will sum up to 10, and the middle digits will sum up to 8, as you can see here. Or the other possible result is that the first and last digit will sum up to 9, and the middle digits will become the number 9.
So Kenneth's pattern before does also work for any number of digits to do the borrowing concept. As you can see, one of the possible outcome that Kenneth has said is the first and last digit will add up to 10, while the next subsequent 2 digit will add up to 8. Similar pattern will be shown for any number of digits. And the other possible outcome is when numbers in between are the same, and the result will show that the first and last digit will add up to 9, while the numbers in between will be 9. Now we've created this by using a program to analyze the patterns in the iterations it will take to reach a constant. Now AP represents the first 2 digits, while CD represents the last 2 digits. And the color indicates the number of iterations to reach the constant. The darker it is, the more iterations. And according to the diagram, the pattern shows that it can be reflected at the line y equals to x.
These are the patterns for the 3, 5, and 6 digits. These are a portion from the original picture.
So we also tried modifying the Kaprekar routine to break it down even more. So first thing that we tried is excluding the leading zeros.
And from there, we undergo the Kaprekar routine itself. But for the second interpretation is that we remove the zeros from the leading zeros. As explained here in the example, is that 0999, we remove 0 and the result will become 0. There are at least 9 combinations with 2 iterations to reach the number 0. This applies for all number of digits.
Okay, so we also tried examining when we exclude all zeros. For example, within the number 200, as you can see, there is a 0 in this. But since we try to exclude all the zeros, then we can exclude that. Therefore, it becomes a digit number. Now, we've tried to find all the possible combinations of those types that will result in an n-1, which in case for a 4-digit is a 3-digit. And this is done by setting all the possible subtraction to 0. Now, when we set that 0, for instance, when we set the third digit to 0, there is one possible combination to become a 3-digit, while setting the second largest 0 will have 70 possible combinations. And it's not possible for the largest digit. As a result, the total number of combinations for a 4-digit number to end up being a 3-digit number after Kaprekar's process, excluding the zeros, is 71 combinations. Here, as I've explained, there are 71 combinations for a 4-digit number to reach 3 digits. And if we do the same thing for 5-digit, we can find that there are 150 different combinations to reach 4 digits. Okay, so we've also tried to compare why the 3-digit and 4-digit number would add up to a constant instead of going through a loop. And we found out an astonishing result. And the reason why they do this is because all the numbers in 3-digit, in fact, all the numbers in between are aligned. As an example, here, B, D, and C are all aligned, and E are all aligned except for A and F, which is the largest and smallest digit. If we apply using this rule, it will always result in a constant. Now I'm going to show another example for this concept. So, as I've said before, a 3-digit Kaprekar routine, normal Kaprekar routine, would result in a constant because the middle 2 digits are aligned, where only the last digit are different positions. Therefore, for 5-digit, it won't reach a constant because there are several values that are not aligned. And this is also an example that shows it will reach a constant regardless of how random it is, as long as all the middle values are aligned. So let's go back. Kenneth will explain the arrangements.
So these are the possible arrangements that leads to a constant from the previous rule that Brian has explained. So from that we get there n factorial over 2 for the possible arrangement, and for the distinct constant that reaches from the arrangements are n times n negative 1 over 2. And what this mean by distinct constant is that the first and second arrangement, as you can see from the example there, is that they both result in the same constant. It's because the first and the last digit subtraction are all in the same alignment and the same position.
So since we've used the rules, we figured out a lot of pattern, including there are only 3 possible methods for applying the Kaprekar routine that we've just established that reaches a specific constant. And those are the types 495, 450, and 8910. 8910 is only for 4-digit and above. And 495 is only in base 10, but the constant formula is shown in the slide here, and where R refers to the base, and for odd base, instead of reaching a constant, we'll reach a loop length of 2. And for the type constant 495, it is done when the largest and the smallest, the first and the last position. Well, 450 produces this constant when the largest and the smallest digit are directly next to each other, which leads to n-1 possible arrangement to the type 450. And this formula can also be used for any number of digits. For 8910, it starts from a 4-digit number and can also be used for any number of digits. And this is when the largest and the smallest digit are in any distance apart, except for when they're in the first and the last, or when they are directly next to each other.
Now these are the formula to get the amount of iteration it takes to reach the constant. Now this for the 450 and 495, they both have the same formula for the even and odd digits, whereas x here is the largest digit and y here is the smallest digit. Now separate from that is that the constant 8, 9, 10, whereas the first one will be 1 and the other one will be 0.
And just to note, there is still a mysterious aspect for a 4-digit Kaprekar constant, since it does not follow our rule mentioned. However, it still reaches the constant. This is why there are still mysterious aspects that 4-digit Kaprekar constant produces. So to conclude, Kenneth will conclude our.
And from there, the Kaprekar routine is they have a simple method and a simple algorithm, which appealingly it seems very simple. But however, from the result we get various patterns within it and the number theories within it. From there, we observe and obtain a constant formula and iteration formula from it.
So these are our references, and these are our works after the first iterations, and these are our computerized output for 5 and 6 digit, and these are our the diagram, the program that we make the diagram. So thank you for listening.